Imagine a world where the worst-case pessimism of adversarial online learning meets the idealized simplicity of stochastic settings, not through compromise, but through a clever bridge, the random order model. In this model, an adversary chooses the full set of data, the multi-set of loss functions, in advance. But the order in which they arrive is completely random. This subtle twist unlocks powerful guarantees. It preserves the robustness of the adversarial regime while allowing us to exploit randomness to avoid worst-case traps. And now, we're about to dive into a breakthrough that transforms how we think about regret in this setting. Let's start with a foundational idea, the batch-to-online transformation, introduced by Dong and Yoshida in 2023. Their insight was simple yet profound. If you have an offline algorithm that gives a 1 plus $verpsilon dollar approximate solution to a problem, and that algorithm has bounded average sensitivity, meaning its output doesn't change much when you remove a single data point at random, then you can use it iteratively in an online setting. You run the offline algorithm on the data seen so far, use its output as your next prediction, and repeat. This simple loop, feeding the past into the future, yields a 1 plus $verpsilon dollar approximate regret bound. But here's the catch. This bound depends on $verpsilon dollar, and it's only approximate. What if we want a standard regret bound? One that compares directly to the true offline optimum, not a slightly worse one. That's where our work comes in. We ask, can we get a small loss regret bound? One that scales with the offline optimum opt dollar, in the random order model, without assuming smoothness or linearity of the loss functions. And the answer is yes, and here's how. The key lies in adaptive tuning of $verpsilon t dollar, not a fixed constant. Instead of fixing $verpsilon dollar, we let it evolve over time, based on what we've seen so far. But choosing $verpsilon t dollar optimally requires knowing opt t dollar, which we don't. It's hidden in the future. So how do we do it? We use a powerful mathematical tool, the concave conjugate. Let's define $verpsilon dollar as the function that quantifies how the average sensitivity of your offline algorithm grows as $verpsilon dollar shrinks. For example, in many problems, $verpsilon sim $verpsilon minus $3, the better the approximation, the more sensitive the algorithm becomes. Now define the concave conjugate of $dollar as $star u equals $inf $verpsilon jec0 left u $verpsilon plus $verpsilon right . This function has a beautiful property. It's the tightest convex lower bound on the trade-off between approximation error and sensitivity. And here's the magic. Our small loss regret bound is $y tilde o star opt t dollar. That's it. No smoothness. No convexity. No self-bounding. Just the structure of your offline algorithm. Specifically, its average sensitivity as a function of $verpsilon dollar. Let's unpack this. Suppose $verpsilon, see $verpsilon q dollar, which is common in many problems. Then $star, u sim uq q plus $1. So the regret becomes y tilde o left, opt tq q plus 1, right. For instance, if q equals $3, we get y tilde o, opt t3 $4. That's a small loss bound. It automatically adapts to benign inputs where the optimal loss is small, giving logarithmic or polylogarithmic regret when opt t dollar is constant. And crucially, this is not just a theoretical curiosity. It's a general framework that applies to a wide range of problems, as long as you have a stable offline approximation algorithm. Now let's see it in action. Case 1, online submodular function minimization. This is a classic hard problem. Submodular functions are discrete, non-smooth, and often not even convex. Traditional methods fail, but our framework shines. We use 1 plus or minus epsilon cut sparsifiers for submodular hypergraphs, a recent breakthrough by Kenneth and Krothgamer, 2024. These sparsifiers preserve the cut values of all subsets up to a 1 plus $verpsilon dollar factor, using only y tilde o, $verpsilon minus 2, n3 dollar hyperedges. But here's the key. This sparsifier construction has low average sensitivity. Specifically, its average sensitivity grows as $verpsilon equals o $verpsilon minus 3, n3 plus n2 log t dollar. Plug this into our framework. Since q equals $3, we get text regret t y tilde o left, n3 4 left, 1 plus opt t3 4 right. This is remarkable. Even though the loss functions are non-smooth and the decision space is combinatorial, we still get a small loss bound, and it's tight when opt t dollar is constant. In that case, we achieve polylogarithmic regret, without any assumptions on the suboptimality gap. Compare that to Hazen and Kale's earlier result of O, /sqrtnt, dollar under adversarial order, a much weaker guarantee. Case 2, online k-means clustering, low-rank approximation, regression. These problems all have offline algorithms with 1 plus $verpsilon, dollar approximation guarantees, and bounded average sensitivity. For example, online k-means, backslash varf backslash verpsilon backslash sim backslash verpsilon minus 5z15 backslash log t dollar, leading to a regret of backslash y tilde o opt t 5z plus 15 slash 5z plus 16 dollar. Low rank approximation backslash varf backslash verpsilon backslash sim backslash verpsilon minus 3 backslash log t dollar, giving backslash y tilde o opt t3 slash 4 dollar. Backslash L1 regression backslash varf backslash verpsilon backslash sim backslash verpsilon minus 3 backslash log dt dollar, yielding backslash y tilde o opt t3 slash 4 dollar. In every case, our framework recovers and strengthens the earlier 1 plus backslash verpsilon dollar regret bounds and gives a true small loss guarantee. Why is this so powerful? Because it decouples the design of the offline algorithm from the online regret analysis. You don't need to build an online algorithm from scratch. You just need a good, stable offline approximation algorithm, and then you can use the batch-to-online transformation with adaptive backslash verpsilon t dollar. And how do you choose backslash verpsilon t dollar? Here's the elegant rule. Let ut equals backslash frac a0 plus backslash sum s equals 1t backslash frac opt sssht backslash quad backslash textware ht equals backslash sum s equals 1t backslash frac 1s backslash sim backslash log t. Then set backslash verpsilon t equals backslash verpsilon backslash min ut dollar, where backslash verpsilon backslash min u dollar minimizes u backslash verpsilon plus backslash varphi backslash verpsilon dollar. This adaptive choice balances the penalty term, how far your solution is from optimal, against the stability term, how sensitive the algorithm is to input perturbations. And this isn't just theory. It's a generalization of AdaGrad-style step size tuning. In AdaGrad, you set step sizes proportional to 1 slash backslash sqrt backslash sum nabla t, a way to adapt to the geometry of the loss. Here, you're adapting to the geometry of the offline approximation sensitivity trade-off. The concave conjugate is the bridge. A word on lower bounds. Is this too good to be true? Not quite. We do have limits. In the adversarial setting, small loss bounds are impossible for submodular functions. An adversary can force linear regret even when opt t equals. But in the random order model, we can achieve them, because randomness breaks the worst-case structure. And we have a lower bound. No algorithm can guarantee O backslash sqrtn backslash c dot opt t dollar regret in the random order model. Our bound of backslash y tilde o n3 slash 4 opt t3 slash 4 dollar leaves a gap, and closing it is a fascinating open problem. Final thoughts. This work reveals a deep connection. Average sensitivity is not just a measure of stability, it's a resource for online learning. By quantifying how sensitive an offline algorithm is to small input changes, we unlock the ability to adaptively tune approximation quality, and thereby achieve small loss regret in settings where traditional methods fail. And this opens a new frontier. Sparsification, sketching, coreset construction, cut approximations, these are no longer just tools for offline computation. They are enablers of adaptive, robust online learning. So the next time you face a non-smooth, combinatorial, or hard-to-approximate online problem, don't despair. Look for a stable offline algorithm. Then apply the batch-to-online transformation with adaptive backslash verpsilon t dollar. And let the concave conjugate do the heavy lifting. Because in the random order model, the future doesn't have to be adversarial. It can be learnable. Thank you for watching. If you found this insightful, consider subscribing for more deep dives into the cutting edge of online learning and algorithmic stability.